Today, our first experiment, this experiment, what you are going to today is load flow studies. In that, we are going to see the two algorithms. First one is Gauss Seidel method and Newton-Raphson method. First, I will explain you the algorithm and followed by the program, and we'll try to simulate. You also, if you are having Matlab in your laptop and if you are having Matlab in your desktop, you also open and keep it ready. I will share you the program also, and you can simulate and you can show the result. If not, I think you can also online Matlab also there. Just type in Google online Matlab simulation. For students, they are giving free access to simulate for program. Few things you can simulate, but all things you can't do. But a basic program you may run and you can see the output. That guarantee I'm giving you. That also you can copy paste and you can simulate it and you can analyze the code. First, coming to the Gauss Seidel method, the basics, I will share you the link, video link, that you can just study the basics. Now I'm directly going into the algorithm because of the time concern. Gauss Seidel algorithm. The following procedure for Gauss Seidel method. First, you need to formulate the YBus matrix. As I said in our class, first formulation of the YBus matrix is very important. Not by bus building algorithm, by direct inspection method. You need to formulate the YBus matrix. The second step, you need to assume the flat voltage profile. Or otherwise flat start. We can also call it as flat start. That is initially assume the value of voltage magnitude as 1 at the phase angle of 0. That is V is equal to 1 plus J0. That means you are sending full power. Say, for example, your generator size is 11 kilovolt or 25 kilovolt. It is default, meaning it in the sense you are sending the full power. That is 11 kilovolt you are sending, and your 11 kilovolt means not 11 kilovolt. That is step up into 400 kilovolt or 750 kilovolt like that. But the default meaning for this flat start is you are sending the full power. Whatever the generation happening, you are sending the whole power to the transmission line. That is the thing. So we are taking the flat start. V is equal to 1 plus J0 for all the nodal voltage except for the slack bus. Slack bus already given with a problem only. Next step, set the iteration count K is equal to 0 and the bus count P is equal to 1. Check for the slack bus. P is nothing but the slack bus. So increment P. First, we are starting with the bus count P is equal to 1. Next, meanwhile, we are incrementing the slack bus count. Next, step number 4, for the bus P, evaluate Vp K plus 1. K is nothing but iteration. So you need to evaluate the Vp K plus 1. So this is the formula for calculating the Vp K plus 1. There is some basic formulation is there, how this equation comes. That also I will give in the comment section. You just go on in your free time, you can watch that video, how this equation becomes. So if I start again, half an hour will go with this. Here, Vp K plus 1 is equal to 1 divided by Ypp, Pp minus J into Qp divided by Vpk, the whole power star. Star is nothing but a conjugate, complex conjugate. Say, for example, if Vp value is 1 plus J0, star means you need to take 1 minus J0, like that. So minus summation Q is equal to 1 up to P minus 1, Ypq, Vq, K plus 1 minus summation Q is equal to P plus 1 up to N, Ypq, Vq, K. This is the equation number 1. This is the formula for calculating the Vp K plus 1. Next, step number 5, we need to calculate the change in the voltage. Change in the voltage or voltage difference. Change in the voltage del P K is equal to Vp K plus 1 minus VPK. Now, what we need to do is we need to advance the bus count by 1 and check for all the buses that have taken into account. If yes, go to the next step. Otherwise, go to the step 3 and continue this same. Okay, so the bus count is 1 means that's all. Up to this step, you need to calculate the voltage and the change in the voltage. If the bus count is 2, again, you need to check for the bus count and we need to increment the bus count. So if yes, go to the next step. What is the next step? Find out the largest of absolute value that is change in voltage. So largest of absolute value, that is a VP accelerated value, or we can also call it as VP new value. In some books, in some materials, it is mentioned as a VP new value or accelerated value. Both are same. Here, notation only different. So VP accelerated value is equal to VPK, that is volt value. In some books, it is mentioned as VP volt. So VP new is equal to VP volt plus alpha into del VP. What is this alpha means? Acceleration factor. This is the process of convergence that can be speed up by acceleration factor and the voltage correction during the consecutive iteration. So acceleration factor, we are taking the value acceleration factor as 1.6. So accelerator factor alpha is known, that is acceleration factor, that is a real number. A suitable acceleration factor might be chosen for your problem. Say it is not mandatory like you have to choose only as 1.6. You can choose your own values, but the thing is that your answers, your answer will not be accurate. Yeah, while choosing the acceleration factor, so wrong selection of acceleration factor will slow your convergence value. So convergence value means, say for example, exact value you have to get as say for example 2 plus some 3j. That is the exact value. That is the exact answer you want to get. If you choose some other acceleration factor, say for example, instead of 1.6, I'm taking that's 1. So the convergence will be slower. The convergence will be slower. It means the program convergence. Say for example, instead of 2 plus 3j, that is the value, you will get as 1.8 plus 2.8j. Like that, you will get. The answer will not be accurate, and also the time taken for the algorithm also will be somewhat more. The time taken will be somewhat more, and there will be a divergence in solution. That will be different answers will be coming. So you can also try with this acceleration factor by not taking as 1.6, but mostly they are taking the as 1.6 because this is not a like a golden rule. You need to choose 1.6. What they did is they just trial. It is all trial and error method. They just made this trial and error. First they substitute 1, first they substitute 1.5, 1.4, 1.3 like that. Then with the 1.6 value, the convergence is somewhat faster. Faster. So that's what I can tell. So this is the formula for calculating the VP accelerated value. That VP accelerated value, VP accelerated K plus 1 is equal to VPK plus alpha into del VP. Del VP means this change in the voltage. Change in the voltage. This whatever the answer we are calculating, that you need to substitute over here. So this is the step number 6. So this is already I said. Next, find the V for other buses. Say for example, other buses. Say for example, you need to count the bus, counter the bus to next bus. P is equal to 2 like that. Repeat the iteration till del VP for all the buses. So you need to calculate first voltage and you need to calculate the change in the voltage and you need to calculate the new voltage. New voltage in the sense accelerated voltage. Accelerated voltage or new voltage. Next, you need to set the tolerance limit. Tolerance limit, this is zeta. Yeah, zeta as a tolerance limit. The tolerance also within the limit, you can choose the tolerance limit as 0.0001. This also, it is user defined tolerance limit. You can set any tolerance limit, 0.1 also you can set like 0. The thing is that if you not set this tolerance limit, your program will run for n times. Your program will not stop. As you did, as you seen in your basics of your Python programming and basics of your C programming, without giving this tolerance limit, your program will simply run. It will not display the result. So say what for this tolerance limit? The program will stop at a certain point. It will check the limit, and later on the program will stop. So here we are doing like this: change in the voltage, VPK plus 1 minus VPK less than tolerance limit. Okay, then your program will stop. Evaluate the line flows and print the voltage and line flows. If not, advance the iteration count. Again, you need to go for the iteration count, that is k is equal to k plus 1, and go back to the step 3. Step 3, what you need to calculate again. You need to set the bus like iteration count next iteration count. You need to increment the iteration count, and you need to calculate the voltage, change in the voltage, and the accelerated voltage. Accelerated voltage you need to calculate, or new voltage you need to calculate. New voltage equal to old voltage plus alpha into this change in the voltage. That also you need to calculate for the next iterations. So tolerance limit, it will check this value, then it will stop and print the results. Otherwise, your program will simply run. Next, if the system, the same thing you need to calculate for you did for your this real power. The same thing you need to calculate for reactive power also. Calculate QP calculated K plus 1 is equal to minus imaginary of this VPK the star summation Q is equal to 1 to N YPQ VQ K plus 1 plus summation Q is equal to P up to N YPQ VQ K. So up to this. Okay, so you need to calculate QP K plus 1. This condition, if the system with a PV bus, that is PV known and Q and delta unknown, that time if P and V are mentioned in the problem, then you need to calculate Q and delta. So that basics also I will give that video link in the comment section. You just go and watch that thing. So Q and delta are unknown. Here, what you need to do is you need to calculate. In that case, you need to calculate the reactive power. Reactive power K plus 1. This is the formula for calculating QP K plus 1 calculated value. If QP K plus 1 calculated value is less than the limits, as we did it in our economic load dispatch problem, the limit we checked it in lambda iteration method. The same thing. Similarly, here also we need to check for the reactive power limits. If QP calculated K plus 1 is less than Q minimum, then set QP is equal to QP minimum value. If QP calculated K plus 1 is greater than Q maximum, then set QP is equal to QP maximum value. These are the things. So one problem we'll see later. You can understand this is the very simple problem. 3-bus system. You can also choose 2-bus system also like that. The program is also simple, and you can get the answer in a very less steps. For the specified value of PP real power and set the QP, calculate VP K plus 1, that is voltage value, and find the new voltage, that is VP accelerated value, and proceed to the next bus. So this is the thing. So for the specified value, what we need to do is we need to calculate this reactive power and change in the voltage and the new voltage. That also you need, similarly you need to calculate it for the reactive power also. So this is the problem. You're having 3-bus system, having the admittance values also given in the problem. That is admittance between 1 and 2 is Y12 is a minus 3J. Next to Y13 is a minus 4J. Y23 is minus 5J. So these are the admittance value given in the problem. For the relevant per unit line admittance are indicated on the single line diagram, and the bus table also, data also given in the table below. So here they are given with the bus number and the type of the bus and the generation, like real power, reactive power, and the load also real reactive power, and the bus voltage and the phase angle values they have given. So slack bus, these are all not mentioned. So here they have mentioned as voltage and delta, that is phase angle value. 1.02 is all in per unit. Okay, this is all not in any megawatt or kilowatt amperes, all in per unit. So per unit, what is the significance of the per unit and all already you studied. No need to explain much. Here PQ bus value. PQ bus value also mentioned. PG value mentioned. QG value mentioned. PL value mentioned. QL value mentioned. And this value not mentioned. And again, for the load bus also the value is mentioned here. Determine the voltage at bus 2 and 3 after first iteration using the Gauss Seidel method. Take the acceleration factor as 1.6. That also clearly mentioned in the problem itself. In some problem it is not mentioned. You can defaultly take that value alpha as 1.6. Next, first step, you need to calculate the YBus matrix. YBus matrix, you know. So Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32, Y33. So what is Y1, Y11? So what are all the admittance coming to this bus 1 you need to add? So simply two admittance are coming here. So minus 4J plus minus 3J, that you need to add. That is Y11. Similarly, Y22, here you see two elements are coming to this bus number 2, Y12 plus Y23, that is minus 3J minus 5J, that you need to add. Similarly, Y33, what is here? Yeah, you need to add this two elements, that is minus 4J minus 5J you need to add. So that is Y33. And here Y12 values are also given. Y12 is equal to minus 3J, Y13 is equal to minus 4J, Y23 is equal to minus 5J. So with this, you can simply formulate the YBus matrix. Here we added, and Y11 is equal to minus 7J, and Y22 is equal to minus 8J, Y33 is equal to minus 9J. So YBus formulation matrix we formulated minus 7J, 3J, 4J, 3J. So here all minus of. Here whatever is coming, it is minus of. Here minus 8J, 5J, 4J and 5J and minus 9J. And hope you are also calculating. You just tell in the comment you are also getting the same answer or not. Next, real power. How to calculate this real power? P2 is nothing but P2G, that is second bus 2G minus 2L. That is this formulation. P is equal to PG minus PL. Next, Q is equal to QG minus QL. That is generator minus this load. So this after calculating, that is P2G is nothing but 0.25. P2L is nothing but 0.5. This you just minus this. You'll get the answer as minus 0.25. That is P2 is equal to minus 0.25. Similarly, reactive power Q is equal to QG minus QL. So here after calculating this 0.15 minus 0.25, you get the answer as minus 0.1. Real power and reactive power. Next, P3, that is the third bus. Third bus also mentioned here. So P3G minus P3L. This is all mentioned in the problem only. This is all mentioned in the problem only. It is not a default value. This is all mentioned in the problem. This you need to calculate. That's all. This minus this. That is 0.6 minus 0.3. That is the for a third bus. Here P 3G minus the. So G generator bus not given. So 0 minus 0.6. That is minus 0.6 P3 in per unit. Here also Q3 is equal to Q3 G minus Q3L. Generator value not given, so defaultly you can take as 0. Yeah, load value given, that is minus 0.3, sorry, 0.3. That is at the as a whole Q3 is equal to minus 0.3. This is the Q3 value. Sometimes directly the problem itself will be mentioned. If not, you need to calculate it. Here, what is the next step? You need to, step number 2, you need to start with the flat start. But here, flat start, you can't start because V1 value already mentioned in the problem itself. Already mentioned in the problem, V1 value as 1.02 at the angle of 0 degree. But other voltages, you need to make the flat start. So other voltages, that is V2 naught is equal to 1 at the angle of 0 degree. V3 naught also 1 at the angle of 0 degree. That is flat start. So here this value, this voltage value already given in the problem. Next, what you need to do is you need to set the iteration count. K is equal to 0, P is equal to 2, and Q is equal to 1. Why P is equal to 2 means the P is equal to 1 value already mentioned in the problem. So no need of taking that. So we need to start with the second bus. This is the bus number 2. And the Q you are taking it as 1. So VP K plus 1, this formula already we have seen 1 divided by YPP into PP minus JQP divided by DPK star minus summation Q is equal to 1 to P minus 1 YPQ VQ K plus 1 minus summation Q is equal to P plus 1 up to N YPQ VQ K. Just to substitute K is equal to 0 and P is equal to 2 and Q is equal to 1 in this equation. So you will get the formulation like this. V2 1 is equal to 1 divided by Y22 P2 minus J into Q2 divided by V2 naught, that is initial value, the star minus summation Q is equal to 1 up to 1 because P is equal to 2 here. So Y21 Y1 sorry V1 1 minus summation Q is equal to 3 Y23 here 23 V3 0 K is equal to 0. So is here P is equal to 2. Here P that is bus number we are taking as 2. Sometimes bus number will be 3. So here you need to take 3. So 3 minus 2, 2. So this you need to calculate 2 times. Okay, 2 times. So that because here summation, no. So next also you need to calculate. Like that also you need. So here it is 2 means here 2 minus 1 is 1. So up to 1 only. So only one value will come. So that you need to be very, very careful while solving the problem. Just substitute it, substitute all the values. Already P2 we calculated, Q2 we calculated, Y21 you know from the matrix, Y21 matrix, yeah, Y21, yeah, Y21 or Y12 all are same, 3J. That you need to substitute over here, V1 dash, V1 not, V1 dash or V1 not. So initial value 1.02 at the angle of 0 degree only, minus this value from that matrix. This also you know 1 at the angle of 0 degree. This V2 not star, V2 not star you need to take as 1 minus J0. That is nothing but 1 at the angle of minus 0 degree. So minus 0 degree don't make much sense. So directly 1 you can take. So that's why in some books they have mentioned as simply as 1 here, simply as 1. They will not, sometimes in some books, they will not take this VPK star value itself. Simply they will start with this value or not. That also correct, but the correct procedure is that this is the general formulation. With that, substituting flat start is always 1. So some books, they will not mention this V2 also. So that is wrong actually. but that they need to mention, and you need to substitute that value as one at the angle of 1 at the angle of 0 degree, and star means minus 0. That also you need to be very careful. Don't simply memorize that equation without this thing. Okay, you can do, but that is wrong thing. But this is the generalized equation. Take your scientific calculator and solve it. While solving, you will get the answer as 0.995 minus 0.03125 J. V2 dash. You take as a homework, and you just tell in comment whether you got the same answer or not. Next V2 dash, this is the V2 dash like answer. So next we need to calculate the change in the voltage. That is VPK. VPK is equal to VPK plus 1 minus VPK. So K is equal to 0 here. Just substitute the value V2 dash minus V2 naught. So V2 naught already you know 1 plus J0. V2 dash we calculated now. The same answer. Just substitute here. And further simplification with your scientific calculator, you'll get the answer as minus 0.005 minus 0.03125 J. Next is acceleration factor. Acceleration factor or new value, VP new value. So VP accelerated K plus 1 is equal to, so here K is equal to 0. So here it is 1. So VPK plus alpha into VPK plus 1 minus del VPK. So this is nothing but del VP. That is a change in the, this change in the voltage value already we calculated. So directly you can take the answer here, and you substitute alpha is equal to 1.6 and V2 naught is equal to 1 at the angle of 0 degree or 1 plus J0. So simply I have taken as 1. Further simplification, you will get the answer as 0.992 minus 0.05 J. That is V2 accelerated value or V2 new value. This value you got. Next, similarly, you need to calculate it for the third bus also, because 3 buses there now. So you need to calculate the change in the voltage, and here also you need to calculate the V31. V31 also you need to calculate with the same formula. You just take as homework V3K plus 1. V3K plus 1, you need to substitute all these things here, and you need to calculate the V3 1. So while calculating, you'll get the answer as 0.975 minus 0.067 J. And you also tell in comment whether you got the same answer or not. Here del V3 naught is equal to this minus V3 naught. V3 naught is the flat start that you know. Just substitute it, simplify it with your scientific calculator. You'll get the answer as minus 0.025 minus 0.067 J. That is the del V3 naught value. Next thing is that like VP accelerated value. Accelerated value VP accelerated K plus 1 is equal to VPK plus alpha into del VPK. Del VPK, you know, this is the answer for del VPK. VPK, that is a flat start, V3 naught, that is 1 plus J0. That you substitute, simplify it, you will get the answer as a V3 accelerated 1, that is our V3 new value is equal to 0.96 minus 0.1072 J. This is the accelerated value. So next, you need to calculate the change in the delta value also, the phase angle value also, if it is given in the problem. So as of now, we like in the problem, they asked to calculate only the change in the voltage value and the new voltage value. That's all. So we stopped. Clear all CLC. This is clears your window and clears all your variables. Next, what I did is I have taken the number of buses as n. N is equal to input number of buses, and YBus matrix I have taken directly in the program itself. Actually, this is the wrong procedure. But because for reducing the steps, I have taken simply YBus matrix as directly. But actually, you need to do a small program for this for calculating the YBus matrix. Then you need to include it because in the problem only they have given with only the admittance value or impedance value. Directly while entering the admittance or impedance value, you need to calculate with the YBus matrix. That is a simple logic. You can include this for reducing the number of steps. Directly, I have taken the YBus matrix here. Next, I have entered the slack bus voltage. Input the slack bus voltage, and I'm displaying the enter power negative for load and positive for generation. That also I'm displaying here. I'm making one for loop that is iteration to n. So second iteration, we are starting with the second iteration, and this the text you want to print, you can print it. And here I am getting the real power value. Real power value as P of.
First of all.
Here, I have taken the real power value and reactive power value. P of IT. P of IT is equal to input of real power. Q of IT is equal to input of reactive power we have taken. And I'm formulating a simple if loop. If loop with that reactive power value. If reactive power equal to 0, then Vn specified value is equal to that input of that magnitude of that voltage value that you need to enter. That value you have taken. Else, V specified value iteration of T. Okay, that you need to take it as 0. End. We are making a small loop. So again, I'm taking the tolerance limit. Tolerance limit, that is mentioned in the problem as 1.6. Acceleration factor we have mentioned as 1.6. Here tolerance limit we have taken as 0.0001. You can take your own value, and if you simply take as one also you can take. The thing is that the program will not end. So the thing is that it will compare that a change in the voltage should be less than your tolerance limit. Then only the program will stop. Otherwise, it will run. So don't take as 1. Take as 0.1. 0.1 also sometimes because the change in the voltage we are getting as 0.0 something. So you take as 0.001 like that. Next, I'm inputting the enter the maximum iteration allowed. So maximum iteration you can make it as 10 or 10 or 100 or 2 like that, whichever iteration, because in a problem we are taking only 2 iteration. You can also take 2 iteration. If you enter more iteration, your answers will be good. You'll get an exact answer if you are going for the more iteration. Next, you are making again a for loop for that iteration. So 2 up to n. So n. So iteration, V of iteration 1, that is the flat start, 1 at the angle of 0 degree. So that we are taking, and the del maximum we are taking as 1 first, and that is change in that voltage, that value. And while we are taking another while loop. So you're comparing that and the convergence. The thing is that you need to the change in the voltage. The change in the voltage also you need to calculate for that particular iteration, that particular iteration value. So that also we are checking here and displaying the required convergence was not achieved. If the convergence is you are taking the convergence as less. Next, we are taking the next iteration. The same thing. The thing is that here we are taking the voltage. That voltage, that is V of iteration k plus 1 is equal to 1 divided by YPP into that formula. P minus J into Q divided by conjugate of that V of iteration k star minus sum 1 minus sum 2. Sum 1 minus sum 2 here we have taken, because if you can also take the full voltage value, that is Vp k plus 1, that full we can take. The thing is that more brackets are there, more calculation are there. So what I did is simply I have taken this as sum 1. That alone I am calculating 1, and sum 2, that alone I am calculating. And here I am adding as sum 1 minus sum 2. You can also take it fully, but brackets, you need to do it correctly. Otherwise, if you miss one bracket also, it will take the logic will goes wrong, and it will take the wrong values, and the answers also will be different. And change in the voltage value, voltage value also we are calculating here. For that, we are making one loop. Okay, the voltage value, change in the voltage value. Let's simulate this, and we see. And here also, what I'm doing is displaying the iteration B of iteration k plus 1 is equal to 1 plus A star del, that is change in the voltage. So here, what I'm doing is I'm entering the bus number as 2. As I said before, you can also go for more buses. The thing is that the for loop will increase. The number of sizes in the for loop will increase, and the matrix multiplication. Simply the matrix multiplication also makes some complex. So what we did is we have taken the number of buses as 2 here. Then automatically this already given in the problem, YBus. Next is the slack bus voltage you need to enter as 1.05. This is the different problem again. You can also the problem which we have seen before is a 3-bus system. This is the 2-bus system. Here, this problem also there, time permits, I'll explain. Here, the bus voltage is 1.05, and the bus number, yeah, this and all you are getting in the as an output. That is bus number 2. Real power is 0.3, reactive power is 0.1. That you need to enter, I guess. And also the tolerance limit also you need to give 0.01. Next, acceleration factor also you need to give us 1.6, and enter the maximum number of iteration allow. Simply we have taken as 1 here. Then you'll get the voltage value here 1.05 1, that value here, and change in the voltage for first iteration, second iteration, then the change in the voltage also you are able to display in the matrix format. So here it is in the matrix format. That's why this part you are not getting as infinity value. But answer you need to take this only. That is 1 plus 0.01 I and 1 plus 0 I. That is the answer. And final answer you are getting this. Yeah. Yeah, this is the final answer in the matrix format. So here this is the value you have given. That is from the problem. The final answer you are getting the new voltage as here, and the change in the voltage. Change in the voltage del V. Del V as this. This is the change in the voltage in the matrix format. This is the voltage that is VPK plus 1. That this thing is there now. That. So let's simulate this in the Matlab, and I think yeah, the same formula here I kept. Now we'll simulate this. I hope this window is visible for you. So I already simulated this. Enter the number of buses. Number of buses as 2. Yeah, number of buses as 2 here. Number of buses as 2 here. Yeah, so slack bus voltage, what is the slack bus voltage given in the problem as 1.05. 1.05 is the slack bus voltage. 1.05 is the slack bus voltage. Sorry, 1.05. Yeah. Next, enter the power negative for the load and the positive for the generation for the bus number 2. So power, you need to enter the real power value. Real power as 0.3, reactive power as 0.1. Real power as 0.3 and reactive power as 0.1 here. Next, tolerance limit. Tolerance limit, what we have taken as 0.01. Okay, the same value you also take, and you can try with different tolerance limit value. Let's you see, try with 1, 0.1, 0.01, 0.001, how the result will be. That also you just try, nothing wrong in that, because when 0.01, yeah, 0.01, and acceleration factor 1.6, maximum 901, 0.01, accelerator factor as 1.6. We are sorry, 1.6. 1.6 here we are entering. Here maximum number of iteration allowed 1 we are entering. Yeah. Now you got the voltage value, final voltage value as here. With the this the value mentioned in the problem, that is 1.05 plus 0.001, and for this flat start value 1.01, sorry, 1.01, here also 1.01. This is the voltage value minus 0.1099 minus 0.0082i. That is the voltage value. The change in the voltage value here, change in the voltage value minus 0.6937 minus 0.0051i. So generally, this is the setting end voltage. So what we need to understand from this problem is there are n number of buses will be there. I will explain you. In a power system, in practical power system, there are n number of buses. Say, for example, is visible. Yeah. I am explaining with you with these 2 buses. Say, for example, this is the sending end bus 1 plus J0. 1 plus J0. It is traveling for some distance, say, for example, some 200 kilometers, something. You take some any distance, 200 kilometers, like that, it is traveling. So here you are giving the bus voltage as 1 plus J0. That means some voltage, say, for example, generator size is some 11 kilovolt or 25 kilovolt. You are generating some 25 kilovolt of some 500 megawatt. Okay, 500 megawatt. So that voltage is step up. That 25 kilovolt is step up to some 400 kilovolt, and it is traveling for 200 kilometers. At the receiving end, you'll get some not exactly 1 plus J0. That is in per unit. This is in per unit, no? You will not get exactly as 1 plus J0. You'll get some change in the voltage due to the some losses in the transmission line. You'll get, and also due to the load influence. Say, for example, this is the load bus. Due to the load influence also, there are most of the loads are inductive loads. So due to the reactive power also, there will be the change in the voltage. Slightly change in the voltage. So by giving the voltage as 1.05 plus 0.1i, that is in per unit. So at the receiving end, you will get the value as minus 0.1099 plus minus 0.0082i. So that is somewhat change in the phase angle, and somewhat change in the voltage also. But it is approximately nearer to 1. If you take this, approximately nearer to 1. So this also, so, but there is some losses. There is some losses there. And this is how you need to analyze this problem. So in per unit, if you convert this per unit value into voltage value with the base MVA value, so you will get some answer as some say for example 25 kilovolt you are sending. So that receiving end you will get as some 23.5 kilovolt like that. With say for example some 100 sorry 10 mega amperes or 1 mega ampere, that is the current, and receiving end you will get the current as some 0.995 mega amperes, something like that. The current also will be reduced. So that is how you need to understand this problem. So that's why we are going for this kind of Gauss Seidel method and Newton-Raphson method. There is no golden rule like you need to follow this only Gauss Seidel method or Newton-Raphson method like that. So this is the successful algorithm. This is the successful algorithm. It is invented by Gauss and Seidel. So that's why they named as Gauss Seidel method. This is a successful algorithm. So majority of the we are all following. You can also frame your own algorithm. Say for example, there are some limitations in the Gauss Seidel method and there are some limitations in the Newton-Raphson method. You can frame new algorithm with the overcoming that limitation, and you can put your name also, XY algorithm. That will give you better results for this sending and receiving end voltage, or change in the what is the change in the voltage at the receiving end, or what is the change in the voltage at the what is the change in the phase angle at the receiving end. So that also you can frame, and you can invent your own algorithm.